In this video, I'm going to cover the topic of stability and performance for discrete time systems. So we start with stability. You already know what stability is. You already saw stability in other courses. So what we're going to focus on is actually how to assess stability for discrete time systems. So I already assume that you know the delta epsilon definition of stability. That is basically how you introduce stability the first time. You know how to assess stability for continuous time systems, so looking, for instance, at the transfer function in the Laplace domain, and so looking at the poles of this transfer function, and you know that if the poles are in the left-hand side of the complex plane, then the system is asymptotically stable. So we're going to basically complete this picture and see how these conditions becomes in discrete time. So if we look at the slide, we start with this simple feedback interconnection. So in this interconnection, we have a controller, C of Z, we have a plant, G of Z, on the direct loop. And then we close the loop and we want to assess the closed loop stability of the overall system. In this lecture, we are going to make some assumption, and this mostly to simplify the exposition. So what we assume is that both G of Z and C of Z can be written as a fraction of two polynomials. So we have the numerator of G and the denominator of G, numerator of C and denominator of C. So these are polynomials. The reason is that this implies that basically these are Z transforms or functions that we know, basically the function that we already seen in the lecture on Z transforms. Then the other assumption that we make is that the polynomials, the denominators, dg and dc, so the denominators, are monic. Monic means that the coefficient multiplying the higher power in the polynomial is equal to 1. So this is not an assumption that makes us lose generality, because if we look at this example in which we have this fraction does not have a monic denominator because we have beta of 0 instead of 1 here multiplying zeta. But this can actually be made monic without just doing a simple multiplication and division. So we multiply and divide by beta 0, and what we obtain is this expression. And now we see that the denominator is actually monic. So going back to the slide, the other assumption that we make is that the relative degree of G and the relative degree of C are non-negative, okay? So this means that if we look at a fraction like this, so we see that the degree of the numerator is m, the degree of the denominator is n, then the relative degree of this polynomial is defined as n minus m, and we assume that this relative degree is non-negative, so this means greater or equal than 0, okay? The reason is that, and this will be maybe clear in future lectures when we're going to study the state space representation, but this basically implies that the system is actually a real system. So no physical system can be realized with a relative degree that is negative, okay? Moreover, we assume that the sum of the two relative degrees is greater than or equal than 1. Okay, so we assume that Rg plus Rc is not just not negative, but is actually greater than or equal than 1. The reason is that, again, if you have a bit of awareness of how to go from state space representations to transfer function representation, you should know that a relative degree equal to 0 implies that there is a feed-forward branch from the input to the output. In this scheme that we see here, there is not such a branch. There is not a relation that connects directly the reference to the output y of z. So this means that a transfer function that realizes this interconnection cannot have relative degree equal to 0. Okay? So just to be clear, this can have relative degree equal to 0, this can have relative degree equal to 0, but the sum of the two relative degree has to be at least 1. Okay? But obviously this can be generalized to relative degree greater or equal than 0, adding another branch in the scheme. The other assumption that we make is that the polynomials obtained multiplying the two numerators and the two denominators are coprime. It means that they don't have common roots, okay? So if we go on, we say that the stability and performance of feedback systems, of discrete time feedback system, can actually be assessed looking at the polynomial given here, okay? So stability and performance depend on this polynomial and also on the properties of some transfer functions like this transfer function, this transfer function, and this transfer function. So this is the transfer function between the output and the reference. This is between the error and the reference, and this is between u of z, so the input to the plant, and the reference, okay? And mostly, the majority of these properties actually depends on this polynomial. Okay, the reason why this depends on this polynomial is that this polynomial appears in all these transfer functions. So what is this polynomial? So again, this should not be something new because a similar polynomial is obtained also in continuous time. So to see this, let's look at the board. If we solve our scheme, we see that y of z is equal to g of z times c of z times e of z, and e of z is equal to the reference minus the output, but the output we say is g of z, c of z, e of z. Okay. Now we replace, we solve actually this with respect to e, and then we replace it in y, and what we obtain is that the transfer function y of z over r of z is equal to g of z times c of z, 1 plus g of z, c of z. Okay? Now let's replace the expression with the numerator and denominators for this fraction, and what we obtain is, I'm going to drop the argument z, but we know that these are whole functions of z. So we obtain this expression, then we do this sum, okay? And we also simplify this denominator with that denominator, and what we obtain is this expression over here. So we see that the transfer function between y and r is equal to this, and we know that the stability properties of the system can be assessed looking at the poles of the transfer function. And we see that the poles of the transfer function, in this case, are the poles, are the roots, sorry, of this polynomial here. So if we go back and look at the slide, we have this polynomial that is called a characteristic polynomial. And this characteristic polynomial is exactly the same that you have also in continuous time. So like in continuous time, we know that the properties, the stability properties of the system depends on the location of the roots of this polynomial. And if you think to the Z transform, you know that the root of the denominator will actually be, if you think to a simple pole, the root of that simple pole will actually becomes a power. So depending on where the value of this power, you know, you will have a signal that will decrease to 0 or a signal that will explode to infinity. So you see that in discrete time, if you have a sequence that is the sum of several powers, those powers are actually corresponding to the poles of the Z transform of that sequence. And those poles are actually the roots of this denominator. Before going on, let's look at this expression and let's compute the relative degree of this expression. So since we have dg times dc, we are multiplying these two polynomials. When you multiply two polynomials, the resulting degree is actually the sum of the degree of the two polynomials. Since we know that the degree of the denominator is at least equal, if not greater, than the degrees of the numerators, because you assume that the relative degree of g and c is non-negative, then what happens is that actually the degree of these polynomial is equal to the degree of this multiplication here, of this polynomial here. So if we want to compute the degree of the transfer function, then this degree will be the difference between the degree of the denominator and the degree of the numerator. The degree of the numerator is this plus this, okay? So we subtract this to the degree of the denominator plus the degree of the denominator of c, so dc. And the reason is that this degree will be less or equal to the degree of this, and so we will now actually change the degree of the denominator. So this actually, if we look at this expression, is actually equal to the relative degree of g plus the relative degree of c. And we know that since this is non-negative and this is non-negative, this is actually non-negative. But if we look back at the slide, our assumption is that this sum is actually greater or equal than 1. So this implies that even though this can be 0 and this can be 0, they cannot be both 0 for our assumption. If we go now to the next slide, we see that 1 plus cz gz can be written obviously as the fraction of two polynomials. And again, what we are considering here is the numerator. Because if we go back, we see that the transfer function is c of z times g of z divided 1 plus c of z times g of z. And once we split this in numerator divided denominator, then we see that the numerator of this polynomial is actually equal to this expression here. So that expression now we call it as a general polynomial of degree n. Then we have the result that if the underlying system, linear system corresponding to this scheme, is at the same time reachable and observable, then the stability properties of the system are related to the location of the zeros of this fraction. Moreover, note that by the stated assumption, p of z is monic. This means that a0 is equal to 1. Okay? I want to spend some time on the hypothesis that the system is both reachable and observable. So only if the system is reachable and observable, then the stability properties of the system can be inferred by the location of the roots of this polynomial p of z. This should not actually surprise you. This is a result that you see since the first course in control systems, because it's a fundamental result that if you have a linear system, only the subsystem that is both reachable and observable is the subsystem that produces a transfer function. So a transfer function of a system is not the transfer function of all the linear system, but is only the transfer function of the subsystem that is both reachable and observable. So I will actually explain this in a future lecture, okay? But I will explain this quite quickly in a future lecture because this is something that you should already know, but I will give more details. Now, if we look actually at this property, what we have is that if and only if the system described by the matrices A, B, C, and if we want also D, okay, is reachable and observable, so only if this is true, then it's true that the eigenvalues of the matrix A correspond to the poles of the transfer function between the output and the input, okay? If the system is not reachable and observable, then there are some eigenvalues of A that do not appear as poles of the transfer function. So even though the transfer function may seem asymptotically stable, it's possible that the system, the underlying state space representation, is not actually asymptotically stable because there may be an eigenvalue in A that is not in the stable part of the plane. And we don't see it because it will not appear here. So again, I will explain better this property in a future lecture, but I tell you that this is a property that holds true for both for both continuous time and discrete time, and is something that you should already know. I want finally to spend some time to talk about the property of reachability, observability, stabilizability, and detectability, and the fact that you may know the property of controllability instead of reachability. Then, so in continuous time, reachability and controllability are the same property, in the sense that even though they mean something different, okay, a reachable state is a state that can be reached by another state, while a controllable state, it means that it's a state that you can control to 0, okay? In continuous time, they are the same property. If you can control a system to 0, you can also reach any state in the state space. For discrete time system, the two properties are different. The fact that you can control a state to 0 does not imply that all states are reachable. So this means that in discrete time, controllability does not imply reachability, and there are two different properties. Here, what we are asking is that the system is actually reachable, is the strongest property. Observability, you already know observability in continuous time. Then what about stabilizability and detectability? So let's talk about this property here, okay? If the system is stabilizable, then we can modify this in the following way. So if the system, for instance, is, so we remove this property, but we put stabilizable, then what this implies is that the eigenvalue that we don't see is actually an eigenvalue that produces a stable response. And so if this is stable, the system will still be stable. Okay? If this is unstable, this will be unstable. But it cannot happen if the system is stabilizable, that here there is an eigenvalue that is unstable that does not appear here. Okay? So we see that this property and this property, so detectability is the equivalent of stabilizability in the case of observability. If we have these two properties, obviously these two properties are a weaker version of reachability and observability, but it's enough because we can still infer the properties of the linear system looking at the poles of the transfer function. Okay, so let's go on now and talk about what are the conditions on the poles. So you know from continuous time systems that if the poles are in the left-hand side part of the complex plane, then the system is asymptotically stable. Then if they are on the imaginary axis, then the system is stable or marginally stable if you have simple poles. If you have repeated poles on the imaginary axis, the system will be unstable. And if you have poles in the right-hand side of the plane, then the system will be unstable. How this condition becomes in discrete time? So the condition in discrete time becomes the following, and we can show this easily at the board. Let's look at the first case. So the first case is when all the poles are inside the unit circle. So what does it mean that the pole is inside the unit circle? We know that a simple pole, when we compute the inverse Z transform, will correspond to a power, okay? So in particular, this means that this pole will produce a response of the type P0 power K, okay? Now, this can actually be written in polar form, so we have that this is equal to the absolute value of P0 power K, e power j k, the phase of P0. Now we see that since the absolute value of P0 is less than 1, this sequence converge to 0. This is just a rotation, so you will just make your point rotate, but it will not change the absolute value. So this means that this converge to 0 when k goes to infinity. Okay? So this is the case for the stable, for points that are inside the circle. What happens when we have one simple pole, so one pole on the circle? So if you have one pole on the circle, what happens is that we have P1 power k, and now we have P1 absolute value power k, e, j, k, phase of P1. And now we see that the absolute value of this point is 1. So 1 power k is actually 1, and this is equal to e, j, k, P1 for all k. And so for k that goes to infinity, the absolute value of P1 power k is actually equal to 1. So this means that the sequence will maintain that absolute value, is not going to 0, and is not diverging to infinity. So it's not asymptotically stable because it's not going towards 0. It's not unstable because it's not exploding to infinity. is maintaining this absolute value, basically, this distance from the origin. So this means that the system is stable, or if you prefer a different word, let's call this marginally stable, okay? Then the other case, third case, again an easy case, is when the pole is actually outside the circle. Then we have P2 power k equal to now what we see is that since this absolute value is greater than 1, this power is going to infinity. So all this number goes to infinity as k goes to infinity. Okay? So if the poles are outside the circle, then the system will be unstable. There is a fourth case to consider, and it's the case when we have repeated poles here. So what I mean is that now we have that P1 is equal to P3, and we call just this P. Okay? So here we have two poles in the same point. So what happens is that this is associated to a Z transform of this type. Okay, so this is a transfer function, if you want, that has two poles in P, okay, because it's Z minus P squared, okay, and we assume that P is in absolute value equal to 1, okay? So we are on this circumference, and in this case, in particular, we are on 1, but this doesn't change. So now, if we compute the inverse Z transform of this expression, then we already did something similar when we were computing, when we were doing an example of the inversion integral method. If we go and look at that, you will see that the result of this inverse transform will have the following form. We'll have a certain coefficient that depends on alpha, beta, and p, that multiplies the unit impulse, okay? Then we have C1 that multiplies P power K, and then we have another number, C2, that multiplies K power K, okay? So the inverse Z transform of this function is always something like this for some values of C0, C1, and C2, okay? Now, what happens for K that goes to infinity? Well, for k that goes to infinity, this term is 0, because this term is actually the unit impulse, so is 1 for k equal to 0, and 0 for all the other k's. So this is actually 0, okay? Then we have this term, and this term is a term that we already saw. In absolute value is 1. So the absolute value of this, so in absolute value, this is equal to 1, okay? But what happened to this term? Well, this term is a term that is composed to this, that in absolute value is equal to 1, but we have k, and obviously with k that goes to infinity, this term goes to plus infinity, okay? So we see that the sum of all these is actually going to infinity. So we see that if there are repeated poles on the margin of stability, then the system is still unstable. The instability is different in this case from this case. This instability is faster than this instability, because this instability grows as a power of k. Instead, this instability grows linearly with k. This is exactly the same in continuous time. In continuous time, if we have one pole on the imaginary axis, then the system is marginally stable. If you have repeated poles, then you will have powers of time, t, appearing, okay? And so the system will be unstable. But that instability will be different from the stability of having a pole in the right-hand side of the plane, because that will produce an exponential that is unstable. So the difference also in this case is that the repeated poles on the imaginary axis produce an instability that is lower than the instability produced by the poles in the right-hand side of the plane. Asymptotic stability has some implications. The impulse response of any closed-loop transfer function is bounded and converges to 0 for k goes to 0. So this means basically if you have an asymptotic stable system and the input to your system is an impulse, then the response of the system will converge to 0, okay? Again, this is a property that we already saw in a course on continuous time systems. If you want to think about this in discrete time, you can think that you excite your system with an impulse, the system reach a certain state, but then the impulse disappears because it's an impulse, so it happens only in 0. Then there is not any more excitation provided to your system, and so your system, wherever it is, in whatever state it is, will converge to 0 because it's asymptotically stable. Another interesting implication of asymptotic stability is that any bounded input sequence yields a bounded output sequence. It means that if the input to your system is bounded, for instance, is a unit step, then the output will be bounded. It means that it does not converge to infinity, okay? So it does not diverge. So let's show this with a graph. If we look at this example, we have a system in which this is the transfer function and the input is u of z, and u of z is the transfer function of the impulse. So in this case, this is a signal, so the impulse, that is 0 everywhere apart for k equal to 0 where is 1. The response of the system is of this type. Okay, if the system is asymptotically stable, it will start to move, okay, but then it will converge to 0 because there is not any more excitation after, okay? When instead we have an input that is bounded, okay, so also this is an input that is bounded, but let's look at this one. So when you have any type of bounded input, so it does not necessarily have to be an impulse, okay, let's for instance consider this, then the response of the system, that if the system is asymptotically stable, will be of this type, okay? It will basically be bounded in the sense that it will not diverge to infinity, okay? So you may expect why this is not actually converging to 1. Well, because that property is a property that not all asymptotically stable systems have, and we will discuss this in the next lecture, actually. In general, what happens is something like this. As you said, something like this may happen, or something like this may happen. What for sure cannot happen is that the system goes to infinity, okay? Because the system is asymptotically stable, the input is bounded, the output will be bounded, okay? So this is a nice property, implication of asymptotic stability. So after this discussion, we established that the property of the system, the stability of the system, can be assessed looking at the location of the roots of this polynomial. So how do we assess then the stability of a transfer function? Well, there are various methods. One method is to compute the roots of p of z. Okay, if we compute the roots, we see what the roots are, and depending where the roots happen to be, with respect to the unit circle, then we know if the system is stable or not. Another alternative is that we develop algorithms that locate the roots of p of z with respect to the unit circle, but without computing the roots. So we don't actually need the numerical value of the root. The only information that we need is to know if the root is inside or outside the circle. Another alternative is that we develop graphical methods exploiting the frequency response of the system. So this is again something that you saw in continuous time. In continuous time, you can assess the stability of the system looking at the frequency response of the system. So let's comment on these three different methods. Okay, the first method, that is the computation of the roots of p of z, is actually computationally expensive. It is obviously difficult to compute the roots of a large polynomial. If you have to do it by hand, it's extremely difficult. But also, if you do it using a computer, there will be numerical errors. Much easier instead is to assess if the roots are inside or outside the unit circle. So this obviously requires a criterion that is similar to the route criterion that is developed for continuous time systems. You should already know, obviously, the route criterion. So everything that comes from continuous time is something that you should already know. Just to recall, the route criterion is a criterion that allows you to establish if the root of a polynomial are in the left-hand side of the plane, or on the right-hand side of the plane, or on the imaginary axis. Okay? The route criterion has been developed in a time in which you cannot actually use a computer to compute the roots of the polynomial. Even today, it's preferable to use a criterion similar to route than to find those roots. The third method is the sketch of the graph of the frequency response of the open loop transfer function. The problem of this method, as we will see at the end of this lecture, is that the frequency response is a transcendental function. It means that there are exponential in the function, and so it's actually difficult to sketch such a graph. So for these reasons, the best method that we have is the second method, so to try to develop a method that is similar to the route criterion. So let's develop an equivalent of the route criterion. So we consider the polynomial p of z, okay, and we introduce the bilinear transformation defined by z equal to 1 plus w divided 1 minus w. And this transformation can be inverted, and w is equal to this expression over here. Okay? So what is a bilinear transformation? If we look at this expression and we multiply on the left and right for the denominator, we get this expression over here. And then if we order it, we get this expression. Now, this is a bilinear transformation because this polynomial in the variable z and w has the following property. If we consider z and we substitute z with a constant, so let's say that z is constant, okay, then what happens is that this becomes an equation in which z is constant and w is the only variable. And you see that this is actually the equation of a line. Okay, so this is a linear equation with respect to w when z is constant. If instead z is not constant but w is constant, so what happens is that now w is constant, z is a variable, and so this becomes a line with respect to z. So it's linear with respect to z. So a bilinear transformation is a transformation that is linear with respect to one variable when the other variable is constant. Okay? So this bilinear transformation has the property that maps the set of points that satisfy this equation into the set of points w that satisfy this other equation, and the set of points z that satisfy this equation in the set of points w that satisfy this equation, and so on. This means that the inside of the circle is actually mapped in the left-hand side of this w plane, and the circle is mapped on the axis of this w plane, and the external part of the circle is mapped on the right-hand side of this w plane. So you already understand that actually if we use this mapping, so if we go from the z domain to the w domain, then we can use the route criterion, because the route criterion on w will tell you where these roots will appear. And if the roots appear on this side of the plane, then it means that the z roots corresponding to those points appear inside the unit circle. So let's see the proof of the fact that the W transformation, this bilinear transformation, maps points in this way. So let's consider the absolute value of z. Okay, so the absolute value of z is the absolute value of this expression here. And w is a complex number, so we call the real part sigma and the imaginary part omega. So we replace this in this expression, and then we compute the absolute value. So the absolute value of this number is defined in this way. Now, when the absolute value of z is equal to 1, it means that the numerator has to be equal to the denominator here. So we have this expression, and this expression implies, once we do all the simplification, that sigma is equal to 0. If we now look at the expression absolute value less than 1, then we have that the denominator has to be greater than the numerator, okay? So we want to solve this inequality, so we simplify this expression and this expression, we simplify the square, we simplify the 1, and then we have that sigma is less than minus sigma, and this is true only if sigma is negative. And similar we have for z greater than or equal than 1. So we have the proof that this transformation maps these three sets in these three sets here. I want to point out that this is not the only bilinear transformation that has this property, but actually there are many other that we will see in the rest of the course. So this, for instance, is an example of another transformation that has that property. And this transformation actually is a better approximation of the z-plane with respect to this bilinear transformation. However, while this increased accuracy that we have here is important for control purposes in the next lectures, and so we will use this, for what concerns assessing stability, this transformation is enough. So there is no need to use a transformation that provides a better accuracy, but more computational difficulties, because we see that the relation becomes a bit more complicated. So we have to understand that this relation is an approximation of the z-plane. So the reason why this is an approximation is explained here in this slide. So the w-plane is similar to the s-plane, but is not equivalent. And how this w transformation is obtained is given here. So the real mapping one-to-one in the first, in the primary strip is given by the relation z equal to e power st. Now let's write this exponential in this fancy way. Okay, so this is the same result basically. If you want to write it in this way, you can multiply and divide for e power minus st over 2. So we compute now the Taylor expansion, and we cut the Taylor expansion to the first term with the variable s. So we cut it here. And so this means that this is actually an approximation. Now, at this point, if we define w equal to st divided by 2, we get our bilinear transformation. So we understand that this bilinear transformation is actually a first-order Taylor expansion of the z-plane. Now that we have seen the properties of this transformation, let's use it. So we replace now z equal to this expression in our polynomial, and we get a new polynomial that now is a polynomial in w. And we note that the roots of the polynomial p of z are in one-to-one correspondence with the zeros of the rational function p tilde of w. So the zeros of this function here are in relation with the roots of this polynomial. And if the roots of the polynomial at the numerator of this expression are in the left-hand side of the plane, in the w-plane, then this implies that the roots in the z-domain are inside the circle. So to summarize this, p of z has all roots inside the circle if and only if the numerator of that expression, so we call the numerator q of w has all roots in C minus. The number of roots of p of z in d minus or d plus is the same as the number of roots of q of w in C minus or C plus, okay? Where C minus is the left-hand side of the plane and C plus is the right-hand side of the plane. If q of 0 is different from 0, then also the number of roots on the circle and the number of roots on the imaginary axis is the same. What happens if q of 0 is equal to 0? If q of 0 is equal to 0, this happens actually if and only if one of the roots of p of z is z equal to minus 1. What is the problem with z equal to minus 1? That if we look at our transformation, the transformation is not defined, it's not well defined for z equal to minus 1. Because if we replace z equal to minus 1 here we divide by 0. So this means that we have to be careful, and we always have to check that the degree of this polynomial is the same as the degree of this polynomial. If the degree of this polynomial is less than the degree of this polynomial, it means that there is a certain number of roots in minus 1. Okay? Since we are concerned with asymptotic stability in particular, so we are concerned with roots that are inside the circle, what we want is that the q of 0 is different from 0, and we want to check if the roots of q of w are in C minus. Okay? Now we can use the route criterion to establish stability. So I recall in this slide the route criterion. So again, this is something that you should know already. If you don't remember, I put 2 slides to remind you of this theorem. So let's consider a polynomial, and I wrote this with the variable s, because this works with Laplace, works with the W domain, and so on. So let's consider this polynomial in which we have the coefficients phi0, phi1, and so on, and the polynomial is power of Sn, Sn minus 1, and so on. So we construct a route table in the following way. We write in the first 2 lines the coefficients appearing in the polynomial. So the first line, the first spot is the first coefficient, then the third coefficient, then the fifth coefficient, and so on. On the second line, we put the second coefficient, the fourth coefficient, the sixth coefficient, and so on. Then, let's say that we want to compute the next element of the table, okay? And we compute the generic element at the step I minus 2, okay? So we want to compute L1, where we have already the previous 2 lines. How do we compute L1? So to compute L1, we have to use this formula here, okay? L1 is the determinant of this submatrix, where this submatrix is this submatrix here, divided minus this element here. And then for L2, the formula is this, and in general, for the element Lj, okay, the formula is this one. So it's always the determinant of a matrix in which the first 2 elements are the first 2 elements of the previous 2 rows, and the second column corresponds to the position of the elements that we want to compute plus 1, okay? So it seems weird, but it's actually quite easy to remember, okay? You have to remember the route criterion. It will not be in the formula sheet of the exam, okay? So this is something that you have to know, okay? If you do a couple of exercises, you will remember this formula very easily. So at this point, we use this formula to construct all the table, and the table will, at a certain point, will finish, okay? In particular, the table will have lines from 0 to n, where the last line will be actually a line of zeros. Then we can use the criterion, and the criterion is the following. If the route table is well defined, and this means that the first column are all non-zero except at most the last element. So what we are looking at is the first column now, okay? All the information that we need is in the first column. First of all, if there is a 0 that is not in the last position, then this means that the system is not asymptotically stable. If instead no zeros appear in the first column, apart the last element, then what we have is the following result. We have to count the number of times that the sign changes in the first column. That number of times corresponds to the roots in the positive real part of the plane. And if we count the number of sign permanencies in the first column, then that corresponds to the number of roots with the negative real part. So this implies that a system is asymptotically stable only if the first column is all positive or all negative. All other cases means that the system is not asymptotically stable. If this criterion, this theorem confuses you, well, first of all, this is something that you should already know. So this is not your first course on control systems, and you should already done this theorem in your first course on control system. If, however, you are confused by this theorem because you don't have this in your background, let's look at some example, and we see from the example that actually this is not as hard as it seems, okay, and actually very easy. So let's consider the polynomial phi of s equal to s power 3 minus 4s squared plus s plus 6, okay? So we write the root table, so we write the first 2 lines. So in the first 2 lines we put the coefficient 1, then here we put 4, then here we put 1, and then here we put 6, okay? Then we want to compute the element over here. So let's call this element alpha. So as alpha is defined in the following way. Is the determinant of this matrix, so it's 1 times 6 minus 4 times 1, and then we have to divide this determinant for minus this value over here, and so we have divided 4, okay? So if we do this, is 6 plus 4, 10 divided by 4, okay? And so we have 5 over 2. So this is equal to 5 over 2. Then we have to compute this element over here. And we see that actually this element, to compute this element, we have to do this times this, but here we have 0, minus this times this, that is 0, and then divided by this, but we have 0. Okay, so this element is 0. Then the last element of the table, okay, we have to compute beta. To compute beta, this is defined as this times this, so beta is equal to minus 4 times 0, minus 5 over 2 times 6 divided minus 5 over 2. And so we see that actually this element is equal to 6. Okay? Now, what are the roots of this polynomial? So what we count now is sign permanence and sign changes. So when we go from this line to this line, there is a sign change, so we count 1. When we go from this line to this line, there is a sign change because this is negative and this is positive, so we count 1. And when we go from this line to this line, we see that there is no sign change because this is positive and this is positive, and so here we count 1. So this implies that this polynomial has 2 roots in the right-hand side of the plane and 1 root in the left-hand side of the plane. And this is the case because actually this polynomial can be written as s plus 1, s minus 2, s minus 3. So we see that there are 2 roots in the right-hand side of the plane and 1 root in the left-hand side of the plane. Okay? So if we were checking just the stability of the system, already looking at the first 2 lines, we will know that the system is not asymptotically stable because there is a sign change. So just looking at this without doing any computation, we know that the system associated to this polynomial is not asymptotically stable. Let's make another example. So the next example is 2s power 4 plus s3 plus 3s squared plus 5s plus 10. So we have the first 2 lines, 4 and 3, is 2, 1, 3, 5, 10. Okay? So first of all, we check, obviously here is 0. Okay? Okay, so we want to compute the element over here. So this is 2 times 5 minus 1 times 3. So minus 3 divided minus 1. So this is 10 minus 3, so is 7 minus 1, so is minus 7. So the element that goes here is minus 7. Then we want to compute the elements that goes here. So here there is actually a trick, because the elements that goes here, when here there is a 0, is always the number that appears here. So this is 10. So we can check it. So to compute this term is this times this, that is 0, minus this times this divided minus this. Obviously, it's always this term over there. Okay, now we compute this term would be 0, okay, because this column is both 0. Then we go to the next line. So for the next line, this element is 10 minus 7 times 5 divided minus 7, so plus 7. Okay, so we have this expression over there that should be 45 over 7. And so we write here 45 over 7. Now, we want to compute this element over here, but this element will be 0. And now we want to compute this element over here, but this will be this by this, minus this by this minus this, so this will be 10. Okay? So we see that there is one change of sign, another change of sign, so 2 changes, and there is 1 permanence and 1 permanence, so 2 permanences. So this means that there are 2 roots in the right-hand side of the plane and 2 roots in the left-hand side of the plane. Let's make a last example. In this last example, we have something a bit different, a problem that is a bit different, and actually is something that may happen quite, that happens quite often in the exercises and in the exam. So we have a polynomial in which one of the coefficients is not determined, so it's k. So the question is, what is the value of k for which this polynomial has all the roots in the left-hand side of the plane? So to solve this exercise, we construct the route table, so 4, 3, 2, 1, 0, okay? And so we have 1, 6, 11, 6, k plus 2, okay? Then we construct our table. So the element here is 6 minus 66, so it's minus 60, divided minus 6, so it's 10. Yeah. Then the element that goes here will be k plus 2, okay, because as I said for the trick of before. And now we want to compute this element here. So this will be 6k plus 12, that is this times this, minus 60, divided minus 10. So this is actually equal to 6k minus 48 divided minus 10. Is there a nicer way to write it? No, this is it. Let's write it as 48 minus 6k divided 10. And for now, this is fine. Okay, so we call this alpha, and this is alpha. And now we want to compute the term here, but the term here will be k plus 2. Okay. Now what we want is that all the roots are in the left-hand side of the plane. It means that we want that all the first column has the same sign. This is positive, so this has to be positive, and it is positive. This has to be positive, and it is positive. Then we want that this number is positive, so we want that 48 minus 6k divided 10 is greater than 0. And then we want that this term is positive, so we want that k plus 2 is greater than 0. So we have to solve this system of inequalities. To solve this, so we see that here we can eliminate 10, and here we have minus 6k greater than minus 48. So this implies that k is less than 48 divided 6, okay? And then this is equal to 8, okay? And then we have from here that k is is greater than minus 2, okay? So here we have that k is between minus 2 and 8. So we have solved the exercise. For all values of k such that this condition is satisfied, this polynomial has all roots in the left-hand side of the plane. In this way, we have solved this exercise in a very easy way. If you want to compute the roots of this polynomial, that starts to become very challenging, and it becomes very difficult to establish for which value of k the roots of this polynomial are in the left-hand side of the plane. But with route, this becomes very easy.
Another method to study the stability of discrete time systems is to analyze the frequency response of the system. Okay, so let's start to define this frequency response. Let's recall how the frequency response is defined for continuous time system. So in continuous time, we will have the Laplace transform, that is g of s, and the frequency response is basically g of s computed at s equal to j omega. Okay, so the frequency response will be equal to g of j omega. Okay, how we can translate this for discrete time system? So in discrete time transfer function, the pulse transfer function is g of z, and then we remember that the relation between continuous time and discrete time is that z is equal to e power s capital T. So if computing the frequency response in continuous time boils down to replace s with j omega, then this means that to compute the frequency response in discrete time, we have to replace z equal to e power j omega t in the function g. So we obtain that the frequency response is the function g of e power j omega capital T, where omega goes from 0 to pi over capital T. And the reason is that we have to remember that the information that is actually useful is just the information in the primary strip. So obviously this is just half of the primary strip, and the reason is that since we are talking about frequency response, this makes sense only for positive values of frequency, and so we are looking just at the positive part of the primary strip. But this is a very important aspect, the fact that the frequency response for discrete time system is defined only for these values of frequencies. Okay, it doesn't go up to infinity like the frequency response of continuous time systems. Then we can notice the following facts about the frequency response of discrete time systems. So the frequency response is a transcendental function. So a transcendental function is a function of where exponentials appear. Okay, so the reason is because we have this exponential over here. So this is different with respect to the continuous time, in which in continuous time the frequency response is a fraction of polynomials. This makes the frequency response for a discrete time system a much more complicated object to study and to analyze. In particular, the body plot becomes quite tricky to use, because basically the body plot is useful because we can use the logarithmic scale, and this allow us to see a lot of frequency in little space. But since in the discrete time domain we have exponentials, basically the logarithm and the exponential cancel out. And what will happen, what we will see later on when we will work with a body plot, is that for high frequency, there will be a lot of high frequency oscillations, okay? And this is due to this exponential, and is connected to the problem of folding and all the problems that we have discussed in the lecture on sampling reconstruction. Then, if we want to sketch the frequency response, there are some interesting aspects some interesting properties that we can exploit to sketch this function. So the frequency response is defined only for values of frequency in this range, and it is periodic of period omega s equal to pi over t. Okay. And another interesting fact is that we can sketch also the frequency response for negative values of omega, and this is useful when we want to sketch the Nyquist diagram. And for negative omega, we can see very quickly that actually the value of the frequency response for negative omegas corresponds to the complex conjugate value of the frequency response. Okay, so these two relations are useful to sketch the frequency response. Then, like in continuous time, if the system is asymptotically stable, then there exists a relation between the frequency response and the steady-state response of the output of the system to a sinusoidal input. Okay, so this is an interpretation of the frequency response that is true also for continuous time systems, and is true also for discrete time systems. I will talk better about the steady-state response in the next lecture about performance, but basically the steady-state response is the response of the system, so it's the behavior of the system for a large value of time. Okay, so when k is very large, the system behaves in the following way. So if the input of the system is a sinusoid, then the output of the system will be a sinusoid, and the important bit is that they have the same frequency. Okay, so this means that the only difference is the absolute value and the phase, and this is exactly what we sketch on the body plot. Okay, we plot basically the absolute value and the phase of our frequency response. Okay, so the body plot can be interpreted basically as looking at the absolute value and the phase shift of the output of the system at steady state when the input is a sinusoid. Now, the frequency response can be used to study the stability of the system using the Nyquist criterion. To do so, we consider a discrete time system in open loop. So the f of x is the open loop. And then we close the loop and we consider, for simplicity, the case of unity feedback. Okay, so there is basically nothing on this branch of the loop. Okay, so this is the type of systems that we are going to study. Okay. We consider the image on the complex plane of the frequency response of the function f of e power j omega t computed between basically in the primary strip. Okay, so we are studying the primary strip because again there are issues and problems on not be able to distinguish between primary strips and secondary strips when we are not in the primary strip. Okay, so we can sketch this function only for these values of frequency. And this image is called the Nyquist diagram. So what does it mean, the image of the frequency response? It means that we can select one point, omega 1, and then for omega 1, we compute f of e power j omega 1 capital T. And this is a complex number that will have a real part and an imaginary part. Okay, and so we sketch that real part and imaginary part on the complex plane, and we'll get a point here. Okay, then we take another point and so on, and so we will get a graph that can be something like this. Okay, so this is basically the Nyquist diagram. So it's important to note that if f of z does not have poles on the unit circle, then the Nyquist diagram is a closed curve. Okay. If instead f of z has poles on the unit circle, then the Nyquist diagram contains the point at infinity. Okay, so it means if we want to do a sketch like this, okay, that maybe we have a Nyquist diagram that does something like this, and then since in this example f of z has poles on the 0, then there will be a connection between these two branches at infinity, so very far away from the origin. Okay. So for instance, here we have two different Nyquist diagrams for two different functions. Okay, so we have here the Nyquist diagram in which the function is the plot is closed and is all close to the origin. So this is associated to an f of z that does not have poles on the 0. So f of z, no poles in the 0. In this other case, instead, you see that the Nyquist diagram goes to plus infinity and minus infinity over here, and this basically will correspond to the fact that there will be a connection at infinity. So this means that this f of z has at least one pole in the 0. Okay. Now we can use the Nyquist criterion to assess the stability of the system. Okay, so we consider the function f of z, and the first version of the criterion, okay, we assume that all poles of f of z are in D minus. So the open loop transfer function is as poles in the good part of the plane. Okay, now what we want to know. Okay, there is an exception, and the exception is that there may be one or two poles at z equal to 1. So we can allow up to 2 poles in z equal to 1. Okay, if there are more than 2 poles at z equal to 1, then this criterion does not work. Okay, so if all the poles of f of z are inside the unit circle, then the closed loop system is asymptotically stable if and only if the Nyquist diagram does not encircle the point -1 j omega. So this means that if it's true that the open loop system is asymptotically stable, then the closed loop system is asymptotically stable if and only if the diagram does something like this. Okay, so it does not go around -1. For instance, it may do something like this. Okay, so also in this case, it's not encircling, it's not going around -1. If instead we have a diagram that, so here we have the point -1. If instead we have something that does like this, so we see that the diagram is going around -1, then this means that the system is not asymptotically stable using this criterion. Okay, so I want to point out how we count the fact that we are encircling one. So basically, we start from a point, and usually I start from a point on the real axis, so from here. Then I follow this direction, so the anti-clockwise direction or counter-clockwise direction. So I go in this direction, okay, so I follow the curve, and I meet again the real axis. So since I went around, the point -1 is inside, and I met again the real axis, then I count here one encirclement. Then I continue to follow this, and I see that I meet again the real axis, so I count a second encirclement. So in total we have two encirclements, because at this point we are back at the initial point. Okay, so this diagram has two encirclements around -1. This other diagram instead, for instance, this one does not have encirclement because we're just going down and we're not going around -1. And also this one does not have encirclement because we're just basically going up and down here, but we're not going around -1. Then there is a second version of the criterion that is also, so it's more general, this one. So we assume just that f of z does not have poles on the unit circle, again, apart with the exception of a single or double pole at z equal to 1. Okay, so this is a more general case because we are assuming that f of z, we don't require that f of z is asymptotically stable. Okay, it may have in open loop poles in the bad part of the plane. Now we have a criterion for this case. So the closed loop system is asymptotically stable if and only if the number of anticlockwise encirclement of -1 of the Nyquist diagram is equal to the number of poles of f of z in D+. Okay, so this is a more general version of the criterion. Okay, and it helps us to establish stability in this case, okay, when the open loop system is not asymptotically stable. So I want to point out, if this is not clear at this point, that the Nyquist criterion is basically helping us to assess the stability of the closed loop system, looking just at the information pertaining the open loop system. Okay, so this is the advantage of the Nyquist diagram, okay, of the Nyquist criterion. So if we look back at this example, okay, the question is this system asymptotically stable or not? Well, the answer is depends. Okay, why it depends? Because it depends if it depends on the number of poles of f of z in D+. Okay, so if this system, if f of z that produce this diagram has two poles on D+, then the system is asymptotically stable. The closed loop system is asymptotically stable. Otherwise, no. Okay, so if we look at this other case, so is the system asymptotically stable or not? Well, again, it depends on the number of poles. If there are two poles in D+, then these two systems are not asymptotically stable. And the reason is that we know that these two systems are asymptotically stable if and only if all the poles are in D-. Now let's look at to an example. So there is an issue with this method, and the method is that we have to sketch the Nyquist diagram. And in general, this is not straightforward, especially in discrete time. So if you have a computer, you can do it quite quickly. If you don't have the computer, you have to do it by hand. This becomes a bit more challenging. It can still be done, but it becomes challenging. I'm not giving you here the rules to sketch the Nyquist diagram. And the reason is that the Nyquist diagram, it's a topic that is part of your background, okay? So you do usually Nyquist diagram in the first course of control systems in Laplace domain. So it's something that you should already know, and I'm not going to spend time on this aspect. However, I will give you some indication to approximate the Nyquist diagram. so that you can have an idea more or less how to sketch it or obtain an approximation. These rules, this approximation will not work always, but it will work in the case that we are considering in this course, basically. So this should be enough, an analysis like this should be enough for this course. So we have basically in this example this transfer function here, and then we compute the frequency response. Okay. Now what we are interested in is what happened for a low value of frequency, so for a very small values of frequency, and also what happened for high values of frequency, and how high value of frequency in discrete time means pi over capital T. Okay, so basically we are looking at what happens to the frequency response at the two extremes. So to do so, let's do this analysis. And we start with this case over here. So we look at this function, and if omega is much smaller than 1 in absolute value, then what happens is that we can approximate this with the Taylor series, and we have this guy over here, and something similar over here. So j omega t minus 1 times 1 plus j omega capital T minus 1 over 2. And now these terms and these terms simplify. And so we have 1 plus j omega capital T. And here we have 1 minus 1 half. So we have 1 half j omega capital T. And then we have j omega capital T times j omega capital T. So we have minus omega square T square. Now, since we have that omega is very small, this term does not play a role because it goes to 0 faster than this other term. And then we have 1 plus a very small number, so this term does not play a role. And so this is actually approximately equal to 1 over 1 half j omega capital T. That is the number that we have here. Okay. And let's check what happened for a large value of omega. To do so, we just compute f of e power j omega capital T, and the two capital T simplify. We replace this in our function, and what we get is minus 1 at the numerator, and then we have minus 1, and then we have minus 1 over 2, and this will be equal to minus 1 over 3. Okay, so this is value over here. Then the last bit of information that is important is that we notice that this frequency response is on the real axis, on the negative real axis, only if omega is plus minus pi over capital T. Okay. So this is an important information. So why this is true? This is true because we have this guy over here, and so we will have that the only possibility to actually get a 1 over here is that we have this condition here. And this is important because this means that we can have only basically the situation in which this number alpha is equal to 3 and we computed it. Okay. So this is telling us that if we do an approximation of our diagram and we have the point minus 1 over here, then we have the point minus 1 over 3 over here, we know that for very small omegas, the value of the diagram is more or less this guy over here. So the real part of this is 0, and the imaginary part and the phase of this is minus 90 degrees because there is 1 over j. So it means that the diagram starts from over here, okay? So close to minus 90 degrees and close to the real axis 0, okay? And then we know that the diagram will meet the real axis in minus 1 over 3, so over here. And we know that there are no other intersection with the real axis. So we know that the diagram will do something like this. We do this in MATLAB, and actually we see that this is actually the case, okay? So that the behavior is as expected, okay? So this will continue and will continue to as we sketched it, okay? So is this system asymptotically stable or not? Well, here we have one pole on 1, and this is fine because we can have up to 2 poles in 1. And then we have one pole inside the circle. So we can use the first criterion, and the first criterion it says that there has to be no encirclement of -1. And this is the case because we see that the diagram is actually outside, basically, the point -1. So the diagram is doing basically something like this, and it's not going around -1. So it's not doing something like this, basically. Okay. So this concludes the lecture on stability, and this method to assess stability using the Nyquist criterion is an alternative way with respect to Rao. However, you can imagine that the Rao criterion is actually much more easy to apply than using the Nyquist criterion. But it's important that you know that there are both the Rao criterion but also the Nyquist criterion. And if you have MATLAB, you can use the Nyquist criterion to assess stability instead of using the Rao criterion. So it's important that you know how to use both of them, because especially in continuous time, both of them are very important. Okay. In discrete time, everything becomes more complicated, and we see that the Rao criterion is actually preferable with respect to the Nyquist criterion because the Nyquist criterion is more difficult.